Full screen mode.
In the middle.
Okay, so our next speaker is Tony Pahl at UCLA, and he'll tell us about ionizing photons at Google 3.
Thanks so much. Yeah, hi everyone. I'm Tony. I'm going to tell you a little bit about some projects I've been working on while I've been a grad student at UCLA. So I'm entering my 6th and final year at UCLA, working with my advisor, Shapley, as well as some excellent collaborators here at Caltech, as well as at Davis and UC Riverside, as you can see on the screen, including Yvonne, who spoke earlier in this session. So today I'm going to be talking about reionization. So reionization is the last great phase change of the universe, where the neutral hydrogen in the intergalactic medium became ionized and is thought to end at about a redshift of 6. So while we understand reionization happened, the actual specific timeline of reionization is still under debate. So here I've presented 2 different models of reionization. This is in these curves here. So in the y-axis, we have the neutral fraction of the intergalactic medium, and then on the x-axis, we have redshift. So in a rapid model of reionization, the majority of reionization happens between a redshifts 6 and 8. While in contrast, the slow reionization in the light blue curve, reionization happens more slowly between redshift 12 and redshift 6. So in order to understand how reionization actually progresses, we can parameterize the ionizing emissivity. So the number of ionizing photons that are being injected into the intergalactic medium, we can parameterize it as a function of 3 variables. So we have the cosmic star formation rate density, the ionizing photon production efficiency, and then finally F-escape, or the escape fraction of ionizing photons. So while we have to understand all 3 of these variables to understand how reionization is progressing, I'm going to really focus on this last variable in this talk, which is essentially for all ionizing photons that are produced, how many actually escape a galaxy and go on to ionize hydrogen in the intergalactic medium. So while F-escape is very interesting to study, it's also quite difficult to actually observe. So in order to constrain F-escape, we need direct measurements of the Lyman continuum spectral region, which I've highlighted in orange in this upper spectra of a Lyman break galaxy at redshift 3. So unfortunately, directly observing the Lyman continuum is difficult. As you can see in this lower figure, the transmission of the Lyman continuum as a function of redshift drops off precipitously past about a redshift of 4 or so. So if we want to understand how F-escape, what F-escape is in different galaxy populations, where galaxies we think star-forming galaxies are driving the reionization process. If we want to understand F-escape of galaxies, really the highest redshift we can do those sorts of studies is at redshift 3. So again, how F-escape depends on galaxy properties. So which galaxy populations have high or low F-escape can break this degeneracy of the different reionization models I presented earlier. So for example, the slow reionization model assumes a democratic reionization. So such that reionization is driven by many faint sources with high F-escape values, like the blue galaxies that I've highlighted on the left. Well, in contrast, a rapid reionization assumes oligarchical method reionization, where less than 5% of galaxies contribute greater than 80% of the reionization budget. So in order to look at these questions of how F-escape correlates, or how galaxy properties correlate with F-escape observationally, I'm going to be mainly talking about the Keck Lyman continuum spectroscopic survey. This is a deep LRIS survey of star-forming galaxies at redshift 3. So just to highlight some key results from this survey, it's a really fantastic spectroscopic survey that could not be possible without Keck. So after doing some very careful contamination removal of foreground interlopers, we found 13 out of our full sample of 120 galaxies had significant Lyman continuum detections. And the average spectra of those detections is shown in this upper right plot in black, while the rest of the galaxies that had non-significant line continuum are shown in orange. We also measured an average F escape with a full sample of 6%. And from the average F escape and the properties of the sample itself, we parameterized the ionizing emissivity of galaxies at redshift rate as the value you can see on the screen here. We also found some correlations between F escape and galaxy properties, such that higher F escape was found with greater Lyman alpha total width and lower UV luminosity. So to study these questions in greater detail, we can use actually a subsample of the KLCS that has well-described multiband photometry. So an example of one of the galaxies that has well-described SEDs is shown here on the right. So you'll notice some excellent text data, such as MOSFire and LRIS imaging, as well as a variety of other ground-based and space-based data, such as HST. So using the 96 galaxies in KLCS that have well-described SEDs, we can fit those SEDs for parameters such as stellar mass, star formation rate, UV minus V, and stellar age. So now that we have these properties measured for all these galaxies, we can essentially bin the sample as a function of galaxy property. And then once we have a bin sample, we can take the average spectra of that bin and measure F escape. So just to show kind of how we do this fitting process, I'm showing this is actually the full sample composite. So all 96 objects here is shown in black. So we correct that for attenuation from the IGM and CGM up to the green spectra here. And then we fit a synthetic spectra from BPAS to that observed composite. So that fit is a function essentially of three variables: F escape, the column density of H1, and the EV minus V of the spectra itself. I also really wanted to briefly highlight the fit to the Lyman continuum region here in this subplot, which is a really key constraining factor for it. So now that we've measured F escape of these composites as a function of galaxy property, we can look at some interesting results from this analysis. So here we have F escape as a function of EV minus V. So there's essentially the sample binned into three bins, each of about 36 galaxies. And we can see F escape decreases with increasing EV minus V. So this is really consistent with the physical picture of how we understand Lyman continuum photons escape from a galaxy. Essentially, they're produced in H2 regions of galaxies, and they escape through holes in the neutral circumgalactic medium to then ionizing into the galactic medium. So essentially, F escape is modulated by the covering fraction of neutral gas around the galaxy. And we also think dust is coincident with the neutral gas in the circumgalactic medium, such that the more gas there is, the higher covering fraction, and therefore the lower F escape values. Some more interesting results. F escape seems to be inversely correlated with stellar mass, as you can see in the left plot here. And this is also consistent with results from the FIRE2 galaxy simulations, as you can see in the right, at least in the same stellar mass range that we're looking at. We also see a nice decreasing trend in stellar mass. It's great when our observations follow our models. Finally, also very interestingly, we found no correlation between F escape and stellar age or specific star formation rate, which is really interesting because there's this idea that star formation induces these favorable pathways for Lyman continuum radiation to escape from a galaxy, such that galaxies with low stellar ages or high specific star formation rates, we might see observationally higher F escape values in those types of galaxies. But at least in this analysis, we saw no such correlation. And finally, I want to talk about this really interesting parameter, star formation rate surface density. So this is also thought to be strongly correlated with F escape. So there's actually 35 galaxies in our sample that we can make star formation rate surface density measurements. So these are the galaxies with high enough resolution imaging from HST to make the size measurements required to see how compact the star formation is in these galaxies. So we essentially took this sample of 35 galaxies and made 2 bins out of the sample to try to see if there's any correlation between F escape and star formation rate surface density. So we actually didn't see any correlation from our analysis, but also through this analysis, we discovered that really 17 galaxies per bin isn't quite enough data to bore out relationships between F escape and other galaxy properties. So we really need more high resolution imaging for the KLCS to look at this trend a little deeper. So just to bring it back to those reionization models I discussed in the beginning. So specifically, the oligarchical model has some predictions or some assumptions between how F escape depends on galaxy property, such that F escape is directly a function of star formation rate surface density. And in that model, they also find that F escape should be a direct function of stellar mass, even at redshift 4, as you can see in the pink curve here, which is not what we find, at least in our analysis, for the relationship between F escape and stellar mass. So already lending some credence into discerning between these different reionization models here. Okay, great. So I'll show my summary slide here. So a little bit of extra time, so I'll just go through the main points here. So F escape is a key unknown to our reionization modeling, and understanding the correlations between F escape and galaxy property can distinguish between these competing models. So we looked at 96 galaxies with deep LRIS spectra, as well as multi-band photometry, to compare these, understand the connection between F escape and galaxy property. We found a negative correlation between F escape and stellar mass and EV minus V, and no correlation between F escape and the stellar age and specific star formation. All right, thanks so much. I'll take any questions.
Very nice. If the democratic model is the right explanation, then what is the cause of the rapid increase in the ionization that originally led to the oligarchical model?
That's a good question. I mean, I suppose it could be based upon assumptions for how what F escape is in different galaxy samples that may not be true. So I know specifically one of the constraints they use is the F escape of the KLCS, the average F escape of the KLCS sample, which actually the value they use was not corrected for foreground contamination. So after that adjustment, there could be some differences in that model. But yeah, it's a great question. I would love it. What's that?
What about the onset of AGN activity?
Yeah, that's a good question. Yeah, so the first question was essentially what led the oligarchical model or essentially why is the oligarchical model predicting the reionization evolution that it did? And the second question is what about the onset of the AGN activity? I'm not sure about how the onset of AGN activity would affect these models. Definitely something interesting to look into for sure.
So what kind of star formation history are you using in your SED modeling, and does your results depend on that?
Yeah, that's a great question. So we're assuming a constant star formation history. At least in SED modeling of the sample I've done, I haven't seen a large discrepancy in assuming different star formation histories, but definitely something to quantify for the final paper, which is still in preparation. Great question.
Does the longitude versus alpha relation standard for these galaxy properties as well?
Yeah, good question. So the question was, does Lyman alpha equivalent width change with these galaxy properties? So you're saying like as a function of the SED model properties? Yeah, that's definitely something I need to measure. I assume they're definitely correlated. Like stellar mass is a function, or F escape is a function, or sorry, Lyman alpha equivalent width is a function of stellar mass. So I would definitely think so, but definitely something to quantify.
Great, John.
question and an observation. The question
Sure.
is, in your stats, for the ones that had escape, I stared at it really long. It looked like the metallicity of the galaxies was also slightly different, just based off of the ISM line depths. Is that the case?
So we don't fit for metallicity in the SEDs, we just assume a fixed metallicity. So yeah, I guess it's not a free parameter for our fit for F escape. That's
And then-
part of your question. But
The observation is, you got your slope right relative to fire, but fire still over predicts F escape, right? I mean, it's giving you a factor of 2 more.
yeah,
The-
it's definitely higher.
Okay.
Yeah. It seems to be the case. But yeah, so there's actually also Mossfire spectra for these objects as well. So I think in a future paper, we will be looking at metallicity of these samples as well directly. It should be very exciting. So take a look out for that. I think
Were there any
Naveen read it.
questions online?
No, nothing on slide.
Okay, so, because we're out of time, but you want to talk to Tony or any speakers more, we can do so. Great, let's thank Tony then.